So we're going to go over number 2 from 10.3, just so we can so maybe we can talk about like how it's not quite as terrible as it seems, even though it's kind of terrible. So I'll remind you all the question 2, right? There's like a paragraph. Hemodialysis is a process by which a machine is used to filter urea, blah, 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 blah. And a system of 2 differential equations describing this is given by. So part of reading math is distilling what's important, right? Like you could actually take the time to read that entire paragraph, and maybe you should the first few times when you're doing stuff like this. But eventually, you're going to be able to kind of scan and be like, okay, what's really important here? Sometimes, Sarah with some of this usually often reads the end first. Like if I read the last sentence, I know you can't see it. A system of 2 differential equations describing this is, and then they give you some stuff, and then of course the problem's at the bottom of the page. You have to turn the page to the next page, and then there's a whole nother paragraph, and it says, suppose a few things, and then the questions: classify the equilibrium, solve the initial value problem. So we have so to be able to classify the equilibrium, first have to find them, and then we're going to solve the IVP. So let's write down these differential equations. This is Co-17C. Today is what? February 26th. This is product section 10.3, number 2. So we're given these following differential equations. Now, they give us this setup, but really I shouldn't even write this down. You might not want to write this part down, although you certainly can if you want to. dc dt equals K over V times C plus AP minus BC. And also dP dt equals negative AP plus BC. Personally, I don't love the way they've written this, because if I was trying to write this, I would write all the C things first and the P things second in each equation, because I'm treating C as like my X1, sorry, and P is like my X2, right? And we want to order matters. So I would also say though that before we get to any of the finding things, then they tell us that K over V equals 1 and A equals B equals 1/2. So really, we should rewrite this as dc dt equals 1 times C plus 1/2 P minus 1/2 C, or even better, dc dt equals 1 minus 1/2 is 1/2, 1/2 C plus 1/2 P. Similarly, dp dt is equal to negative 1/2 P plus 1/2 C. I don't know why you would write the P first. I'm going to write it better. dP dt is equal to 1/2 C minus 1/2 P. So our matrix, right? So we've done all the interpreting. This one's kind of nice because they actually gave us numbers, right? You could have done this one without numbers. It'd been terrible. So then they actually, right? So then, oh, did I make a mistake here? I better check this out because I feel like I'm making a mistake. Times looking at, oh, I did make it. Oh, I did make a mistake. It's negative K over V. Good thing we caught that before. I was looking at the grant sentence. So really, that should not be a negative. That should not be 1/2 C. It should be a negative 3/2 C. I was like, I feel like there was a 3/2 in this matrix somewhere. There we go. Much better. So now we want to classify the equilibrium. Well, I want to point out we don't have to spend any time finding the equilibrium here, because we have a usual, typical linear system of differential equations here, where it's 2 equations. They're both linear in our 2 variables. So we know that the only equilibrium is what? What's the only one we get? 0, 0, right? The only, right, if there's going to be 1, that's the one that's going to be typically. For a usual system where you have just a multiple of x1 plus a multiple of x2 and a multiple of x1 plus a multiple of x2. When you get into non-homogeneous or non-linear systems, that's when you get other equilibria. But for a linear homogeneous system of differential equations, you just get the 1. So we want to classify what's going on with 0, 0. And we're going to do the usual thing. We're going to write the matrix. We're going to find all the usual eigenvalue stuff. Now, again, normally, if I was just classifying, I might do the trace determinant method. But since the first question is to classify, and the second question is to solve the initial value problem, I might as well find the eigenvalues, because I know I'm going to need them for the second part of this question. But it's always good to read ahead and be like, what do I actually need to find here? So our matrix A is negative 3/2, positive 1/2, 1/2, negative 1/2. So to find our eigenvalues, determinant of A minus lambda I. I feel like you can stop writing the A minus lambda I and actually just do your matrix minus lambda in the diagonals. So negative 3/2 minus lambda, 1/2, 1/2, negative 1/2 minus lambda. That's going to be negative 3/2 minus lambda times negative 1/2 minus lambda minus 1/2 times 1/2 equal to 0. We multiply this out. We're going to get, let's see, a lambda squared, of course, a plus 1/2 lambda, a plus 3/2 lambda, 1/2 plus 3/2 is 4/2, which is 2. And then a minus 3/2 times a minus 1/2 is a positive 3/4. And for me, yeah, I don't love the fractions. I would probably make the choice to multiply everything by 2. So I have 2 lambda squared plus 4 lambda. 3/4 minus 1/4 is 2/4, which is 1/2, and 1/2 times 2 is 1. You don't have to do that, but you certainly can. I don't think this is going to factor. So let's just go ahead and find the eigenvalues the good old-fashioned way using the quadratic formula. So it's going to be negative b plus or minus the square root of 4 squared minus 4 times 2 times 1 all over 2 times 2. So we're going to get negative 4 plus or minus the square root of 8. Yeah, that's right. Okay, sorry. I'm just looking. No, it's fine. Negative 4 plus or minus the square root of 8 all over 2, which is all over 4. Sorry. Which we can certainly simplify as negative 4 over 4 plus or minus root 8 over 4, which becomes negative 1 plus or minus square root of 8 is 2 root 2. So we can write that as just root 2 over 2. There are eigenvalues. Now, even though I've written it this way, I think looking at it this way is going to make it easier to tell what kind of thing we've got going on. So let me ask everybody. For sure, we have at least one negative or at least one positive. Like, what's it easy to see? Do we have a negative 1, thumbs down? Do we have a positive 1, thumbs up for sure? Which one? Negative, positive. Right, we definitely have a negative 1 because of the negative 1 minus something. Now, what about the negative 1 plus root 2 over 2? Well, it might be easier if we look over here. What about the negative 4 plus root 8? Is root 8 bigger than 4 or less than 4? Less. So negative 4 plus a number less than 4 is still negative. So they're both negative. So they're both negative, which means we have what? Right, stable node. Or if you prefer, you can call it a sink. Cool. So then the other part, we have to actually solve the initial value problem. It sounds like, when they say solve the initial value problem, you think, oh yeah, they do. Like, there should be some initial values, right? We still have to find the eigenvectors first, but the initial values are kind of lame. The initial values are C of 0 equals C sub 0, and P of 0 equals P sub 0. So, I mean, yeah, we're still going to use this, but it's not like the best. So to solve the initial value problem, we need to find the eigenvectors. The great thing about finding eigenvectors when your eigenvalues are irrational like this or complex is you only have to find one of them. If you find one of them, the other one, you just switch the signs of the not nice part. So for lambda equal to negative 1 plus the square root of 2 over 2, let's find the eigenvector. Negative 1, maybe? There's a negative 1 there. And this is definitely where I would always go with the A minus lambda I times your vector equal to 0, right? You've seen me do it the other way, right? You know that I kind of prefer A times V equal to lambda times your vector. That's my preferred way of finding the eigenvector. I wouldn't do that here. It's less good, which means you should probably always do it the other way. I just don't like the other way personally. So we're going to solve A minus lambda I times our unknown eigenvector equal to 0. So we're just going to toss this in. This is where it'd be good to have the other piece of paper in front of me for a second. I'm just going to toss my eigenvalue into that 2 by 2 matrix I wrote before with the lambdas there. So I'm going to have -3/2 minus -1 plus √2/2, 1/2, 1/2, -1/2 minus -1 plus √2/2 times the eigenvector we're trying to find. I don't love the names we have for these. I'm going to call it XY. That's what I usually do. 0, 0. And then I would typically try to use the row that has the nicer coefficient for Y, or for your second thing. I don't know really why. Oh, actually I do, because if you're trying to graph the eigenline, it'd be easier to graph it that way. All right, let's do this multiplication. So first row, first column. So I'm going to simplify this a little bit. -3/2 plus 1 is -1/2. And the minus sign distributes to the √2/2 as well. So it is a minus √2/2. That times x plus 1/2 times y equals 0. There's my first row with my first column. Solving for y, and let's multiply both sides by 2, because why not? 1/2 y equals positive 1/2 plus √2/2 times x, or more nicely, y equals 1 plus √2 times x. So my first eigenvector here is going to be, x is going to be 1, y is going to be 1 plus √2. And then the beauty here is that you get the other one for free. You change the sign of the irrational part, so you change the plus to a minus. You change the sign of the irrational part, you change the plus to a minus. So there are my 2 eigenvalues and my 2 eigenvectors. Do make sure though, right, if this had been the opposite sign, like if this had been a 1 minus √2, then it'd be a minus plus here. So that the plus here means a minus here, and the minus here means a plus here. So just be careful that you make sure the signs are correct. All right, now we actually have to write out this general solution. I should say, is everyone okay with this? The thing I'm saying here, that you can just change the sign of the irrational part, like we're good. Okay, I can say more about it, but really, I mean, what you should do if you're not sure about that is just go back with all the work we did here and change all the signs of the irrational parts. Like you could literally put a minus sign there, a plus sign here, right? Yeah, right. Yeah, and then a minus sign here. That's all we're really doing. Finally, well, not finally, nextly, the general solution, we know how to do that. You've just got your x of t is equal to c1 e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2. So we're just going to take our eigenvalues and our eigenvectors and use our lovely formula. So there's my eigenvalues and my vectors. So I'm going to get x of t equal to c1 e to the -1 plus √2/2. Kind of gross, times t times v1, which is 1 plus √2. And then your c2 e to the -1 minus √2/2 times t times my v2, which is 1, and then 1 minus √2. This. Ugh. And then after you found your general solution, then we're going to use our initial values, which are not particularly beautiful, to find C1 and C2. So we're going to say, okay, great. So this is x1 of t, x2 of t. So we're going to, or I guess, sorry, I'm using x here because that's kind of my go-to, but sure. Let's call this C of t, p of t. So, right, this is C of t, p of t. These are x of t. So we're going to plug in and we're going to get that C of 0, which is C0, and P of 0, which is P sub 0, is equal to, let's write as little as we can. C1 times, I don't need e to the anything because we're plugging in. Occasionally someone will be horrible and give you like a non-zero initial value for your time. It's awful. Right? Then you have e to the something and you have to deal with that too. Almost never happens. So then we got C1 times 1 plus √2 plus C2 times e to the 0 1 minus root 2. There's a couple ways to deal with this. You could write the matrix and find the inverse. I feel like that's more work than it's usually worth. It's usually easy enough, I think, to just say, okay, I've got C0 equal to C1 plus C2, and P0 equal to C1 times 1 plus root 2, plus C2 times 1 minus root 2. And then take your pick. I'm usually preferring elimination. I don't think elimination is the way to go here because I don't want to really multiply this by like 1 plus root 2 and then add it. I mean, you probably work out fine. Well, let's do the quote unquote easier thing. Isolate one of these and then plug it into the other one. So we'll isolate C1 here. The C1 is going to equal C0 minus C2. We'll plug that into the other equation. So then you're going to have P0 equal to C0 minus C2 times 1 plus root 2 times C plus C2. Oh my goodness, this is terrible. I don't love this at all. And then we're going to multiply it out and try to solve for C2. So P0 equals C0 times 1 plus C0 times root 2 minus C2 times 1 minus C2 times root 2 plus C2 minus C2 times root 2. Collect all this. Oh, look, that's nice. Those cancel out. How wonderful. These don't cancel out. So we've got problems. It's just gross bookkeeping, right? Like this is where you have to be really attentive, right? You want to stop thinking because you're like, oh, this is just terrible algebra, but like this is where you actually have to be super careful. So P0 equals C0 plus C0 root 2. And then I have minus C2 root 2 minus C2 root 2. So I have minus 2C2 root 2. Let's bring that over there. So we have positive 2C2 root 2. Bring that over there. So we've got C0 minus P0 plus C0 root 2. And then finally, C2 is equal to all that, just terrible, divided by 2, or times 1/2. So C2 is 1/2 C0 minus 1/2 P0 plus 1/2 or root 2 over 2 C0. And then you can plug that back into the other one, figure out what C1 is going to be. It's actually not too terrible to plug back into the other one because basically you're just going to change the signs of everything. So C1 is going to be C0 minus all this. So C0 minus 1/2 C0 is still 1/2 C0. And then it's plus 1/2 P0 minus root 2 over 2 C0. Terrible. And then we should be good citizens and plug those back into the general solution to get the particular solution, but I don't want to write all that out. And I know you know what you're supposed to do then, so we're not going to say this. Yes. So over time? I don't think it's really that much faster. It maybe. I don't think so though. That's interesting. That can't be right. Sorry, I'm just looking at something here that seems very wrong. Did I do something totally wrong? Sorry, 1 second here. This seems really, looking at my work here. Oh, I'm stupid. No, I'm not stupid. I've overlooked something dumb. This is where reading the question's really important. Suppose that C of 0 equals C0 and P of 0 equals C0. Not P0, C0. So this should be a C sub 0, not a P sub 0. Which makes things a lot different. Ugh, sorry. We should fix it. Let's try again. So what we really should have had was, yeah, I know, it's terrible. C0 equals C1 plus C2, and C0 equals C1 times 1 plus root 2 plus C2 times 1 minus root 2. I'm still going to do the same sort of thing. I'm still going to plug in C1 equal to C0 minus C2 right there. When I do this, I get, this is why reading the in question is really important. I know I said, but like, you should also be able to skim effectively. Like, I should not have missed that, but I did, because I was like, I thought I knew what it was gonna say, but I didn't read it as carefully as I should have. Multiplying this out, we've got C naught equal to C naught plus C naught root 2 minus C2 minus C2 root 2. And then, oh yeah, I'm looking at plus C2 minus C2 root 2. The C2's cancel, the C naughts cancel, and I've got 0 equal to C naught times root 2 minus a minus is minus 2 C2 root 2. I think we get rid of the root 2, divide both sides of root 2, and 0 equals C naught minus 2C2, or 2C2 equals C naught, or C2 equals 1/2 C naught. And then plug that back in there, and you're going to get C1 equal to C naught minus 1/2 C naught is also 1/2 C naught. That's so much better. So, good lesson in reading the question. And then you can plug this back in. So this should be 1/2 C naught, and this should be 1/2 C naught. And that would be your particular solution. It always feels bad when your particular solution is still like, has got weird constants in it that aren't actual numbers. Like, I'm not a huge fan, but such is life. Okay. Any questions about any of that? With these applications problems, I know the quiz for that got kind of, everybody got freebie on that one, which is great, but it doesn't mean it's not going to show up on your final, right? Like, there'll probably be some sort of application question on your final. Read as carefully as you can. Don't get thrown off by the alphas and betas and thetas and whatever. Like, they're just representing constants. Okay, let's see here. Sure. I feel like we should talk about this Kendrick. I keep wanting to say not the right name. What? I keep wanting to say Kendrick Lamar. I know that's not the name of it, but that's like, I see Ick at the end. I'm like, sure, Kendrick, yeah. Kermack McKendrick infectious disease model. We'll talk about this for a minute. I don't think it's, well, I don't know. I don't know how important your teacher thinks it is. He's obviously spent about a day's worth of lecture on it, so worth some time to him. But let's take a look at the model. So we're given all this. We're given that, and this is the Kermack McKendrick, sure, the Kermack Mick. So we have the following. We have the dsdt is equal to theta minus gamma s minus beta si, right? That's the equation he gave in class. Okay, because there's like a pared down version. Like, if you look in the textbook at problem, what is it? Where'd you go here? At problem 32, they give you a simpler dsdt where you don't have the theta or the gamma s, or they're equal to 0, I guess. And we also are given that didt is equal to beta times s times I minus mu times I. And I'll point out so what are the only things that are counting as variables here? Which letters are variables? Beta is not a variable here. S and I. And technically T as well, but T is not in the equation. Right? The only things that are variables are the things that are over here in your derivatives. So as far as we're concerned, theta, gamma, beta, and my gammas look terrible, and mu are all constants. And they even tell us in the problem there. But even if they didn't, you would know from the way this is written that those things represent constants, because they're not, or at least they're not things we're differentiating with respect to, so, or of. And they tell us, I don't think we need to write this all down. They tell us that theta is the rate of the rate of arrival of susceptible people. Gamma is their per capita mortality rate. Beta is the transmission rate of the disease from the infected to the susceptible. And mu is the per capita mortality rate of the infected people. Okay. So we want to classify some equilibria here? Probably, yeah. So let's go, and we're not going to do this graphically, which is certainly what he was doing in class, at least the video I saw from Friday. He was doing it graphically and kind of talking about, like, if you have different values of, I think it was beta, kind of what happens as far as what your null clients are doing. But let's just look at this in a very non-graphical way, because honestly, I feel like the graphical way is usually, first of all, if you have to use different values of beta, it's really hard to do that, but also just, it can be harder to interpret graphically. Like I've looked at a lot of these graphs, I still struggle being like, well, I think that looks like a saddle, or I think that looks like a stable node. Like it's not easy to tell without lots of practice. Whereas I think the analytical method where we use the Jacobian is more straightforward. Like you can look at the Jacobian and be like, oh yeah, I can see what's gonna happen. So let's do that. So first, let's find the equilibria. Find the equilibria. We're going to set each of these equations equal to 0 and solve for I and or S. So let's look at the second equation first. So beta times S times I minus mu times I equal to 0. I'm going to factor out an I. So I'm going to get I times beta times S minus mu equal to 0. So either we're going to get I equal to 0, or we're going to get beta times S minus mu equal to 0, which would mean that S was equal to mu divided by beta. Yeah. Or not? No, that's right. Okay, yeah, sorry. So plugging those back into the first equation, if we plug I equal to 0 into the first equation, we get theta minus gamma S minus 0 equal to 0. Solving for S, we're going to get S equal to theta divided by gamma. Or looking at S equal to mu divided by beta, we plug that back in up here, things are going to get gnarly. Yeah, theta minus gamma times mu over beta, yeesh, minus beta times S times I equal, oh, not S, sorry, I'm plugging in for S again. S is mu over beta. That's equal to 0. Sorry, that looks a little gross over there. Simplifying a bit, I would probably multiply both sides by beta, to be honest. Like, I don't need those denominators. I know these betas would cancel, but that beta doesn't cancel. So let's just multiply both sides by beta and get theta beta minus gamma mu. That's fun to say. A theta beta is fun to say, I'm not gonna lie. Minus beta times mu times I equal to 0. Solving for I, we have theta beta minus gamma mu equal to I times beta times mu, and then we divide by the beta times mu. Cool. Let's double check. Yep, looks like what they have in the notes. So our two equilibria, I'm sorry, I should zoom back out a second. Our two equilibria are, and let's keep it, so I'm reading this as S first, I second, because we wrote dsdt first. Maybe that's just by chance, maybe that's on purpose, but you should stick with the program, right? If they've written it one way, continue to write it that way. So we're going to say that our S hat comma I hat, because we give little things hats when there are equilibrium. I don't know why. I don't know who picked that, but it's something we do it in stats as well. If you've ever taken the stats class, you talk about the proportion of people that do a thing, and P hat is the sample proportion. Like that's just a notation that gets used. So it's either going to be where'd you go here? Sorry, I equals 0 and S equals theta over gamma. So theta over gamma or comma 0. Or we also have the S equal to mu over beta and I equal to beta theta minus gamma mu over beta mu. You try to write, I should write beta before theta because it comes first in the Greek alphabet. But you could write theta beta. So now, how to classify? Well, one way would be to kind of try to graph these things, but you know, like we could totally do the graphing of the null clients, but it's really hard to do that when you don't have any values, right? Like I could put beta and theta and mu on a chart and try to graph these things, but not super useful, I think. So let's talk about the way I think you should do this. Let's find the Jacobian. So what we're gonna do is we're gonna think of our first differential equation, ds dt is f. So we're gonna think of f of s comma I as the first equation we had, which I know you can't see on my paper here, but I can see it, which was theta minus gamma s minus beta si. And g of si is beta times s times I minus mu times I. And then we're going to find the Jacobian, which is going to be, so here's the way I always remember it. Each row is a different equation. So the first row is f, the second row is g. Each column is differentiating with respect to a different variable. The first column here is going to be differentiating with respect to the first variable, which is s. Second column's I. So it's going to be s, sorry, that's a terrible s there. I, and then the first row, f, and the second row, g. So we're going to do the partial of f with respect to s, which will be 0 minus gamma minus beta I. Minus, this should have made my matrix bigger. It didn't plan very well here. And then partial of f with respect to I is going to be negative beta s. And then the partial of g with respect to s is going to be beta I. And the partial of g with respect to I is going to be beta s minus mu. Beta, yeah, beta s minus mu. All right, then. So now you've got this matrix that doesn't look very helpful. Yeah, let's make sure I didn't do anything stupid here. I will point out all this is in the textbook, by the way. Like this whole example, this is example 2 on page 671 in section 10.4. Right, you can totally look at this later on your own if you wish. Let's go ahead and plug in this first one. So we plug in j of theta over gamma comma 0. Also, if you have questions, you know you're welcome to ask them. Not that you have to have questions, just I want to remind you, like if something seems weird or confusing, I'm happy to clarify something. Plugging this in, so we're plugging in theta over gamma for s and 0 for I. We're going to get the matrix negative gamma minus 0. I don't even need to write a 0 there, but I wrote the minus sign. And then negative beta times s, which is theta over gamma. And then down here, we're going to have beta times I, which is 0. Ooh, I like this. This is good. This is good because it's nice. And then beta s minus mu, s is theta over gamma. So we have beta times theta over gamma. Okay. So let me ask everybody. Let me write this in a slightly nicer way. Here's my matrix. Negative gamma, negative beta theta over gamma, 0. And then we have over here beta theta over gamma minus mu. All of you should be able to tell me what the eigenvalues of this matrix are. What's the easier one to say? Negative gamma. And the other one is whatever that thing is down there. All right, so my eigenvalues are negative gamma and beta theta over gamma minus mu. I should also remind everybody, or have said in the first place, in this problem, we are also assuming that all these constants are positive, right? Because they're all representing rates that would make, right? They're representing the rate of arrival of susceptible people. I guess you could have a negative rate of arrival if susceptible people were leaving, but it's going to be positive. Per capita mortality should definitely not be negative, right? It doesn't make sense for a negative percentage of people, right? That's not a thing. Right, so all constants are positive is stated. So for sure, negative gamma is negative. So this is definitely negative. Now here, let's see what we need to happen. So we would like stability, or at least it'd be interesting to see stability. So if we wanted this to be negative, we wanted beta theta over gamma minus mu to be negative. I would multiply both sides by gamma, say beta theta minus gamma mu less than 0. And for reasons that I found hard to comprehend, not hard to comprehend, but I was just like, why? So in the book, they talk about how the second equilibrium, which is that beta theta minus gamma mu is right. So if you, if you look back over here, if you look at the second equilibrium here, right? So if you look at beta theta minus gamma mu, oh look, beta theta minus gamma mu showing up again. They talk about how, briefly, they talk about how that the second equilibrium is of biological interest only if beta theta minus gamma mu is positive. I don't know why that's true, because I'm not a biology guy, but basically they're saying this system, this second equilibrium is only interesting if beta times theta, so beta, the transmission rate of disease from infected to susceptible, and theta, the constant rate of arrival of susceptible people, minus gamma times mu, which is the per capita mortality times the other per capita mortality. That should be positive. Why? I could not tell you. Like, it's not someone, you should ask someone else to tell you why, because I don't know why. But the upshot is that we are saying that beta theta minus gamma mu should be positive, which means then that, sorry, 1 second. Right, which means that this is not less than 0. So this is actually is positive. And so what do we have here? We have a saddle. We have instability. Which means the disease will spread. Interesting. That's at that equilibrium. What's S and I can remember? S is the what again? Like these letters mean something. S also, S is the susceptible and I is the infected. So if you have zero infected, that doesn't seem right. But I guess it is. Interesting. Yeah, I wonder why that's. Yeah, I don't know. I guess the point is, right, if you're close to, oh yeah, sure. If you're close to that, then you're gonna get pushed away from it because they give you just a few infected people and they're gonna get more infected. Okay. We don't need to actually, I don't need to actually make the biology make sense to myself. You might want to. Oh, papers, come on, papers. Let's look at the other equilibrium, which I might need paper. Okay, the other equilibrium is S hat comma I hat was equal to mu over beta comma beta theta minus gamma mu over beta mu. And so plugging that into our Jacobian at that point, again, not my favorite example here, but okay. It is worth looking at. We plug this in, give yourself some room here. So I'm plugging into negative gamma minus beta I. So negative gamma minus beta times this I here. Gross. This is terrible. Minus beta times S. Sorry, not minus it, but like over here. Minus beta times mu over beta. And then down here, beta times I. Again. Beta times beta theta minus mu gamma over beta theta beta mu. Oh my goodness. Finally, holy smokes, a beta times S minus mu. All right, let's see what that gets us. Let's look at the book. Sure, it gets us not greatness. Oh well. So simplifying, yeah, we have negative gamma. This beta cancels here. I'm going to change the signs and write this. Yeah, I'm going to do that. Oh, yeah. No, I'm not. It's minus beta theta minus gamma theta gamma mu. Holy geez. Okay, I understand why this is terrible. Over here you have a minus mu. Down here you have a beta canceling again, and you're going to get beta theta minus mu gamma over mu. Finally, over here, mu minus mu is 0. And sadly, This is not one of those nice cases where you could be like, oh, the eigenvalues are just the things, right? The zero there is not super helpful. This is where you actually have to like do the work. This is an excellent opportunity to use the trace determinant method instead of trying to actually, right? Finding the eigenvalues here would be terrible. You'd have to do the determinant of a minus lambda I, like that's awful. So let's use the trace determinant method. So the trace is negative gamma minus beta theta minus gamma mu over mu plus 0. The determinant is this, which is 0 minus that. So note, no, let's write it that way. So it's going to be minus mu times beta theta minus mu gamma. The minuses cancel. Oh, sorry, over mu. Don't forget the over mu. So the mu's cancel, the minuses cancel. So we end up getting beta theta minus mu gamma, which I believe we said was positive. From the biological observation that I don't know what that means. So this is positive. Okay, our determinant is positive, which means what? Nothing. I mean, it doesn't mean nothing, but it means that we don't have a saddle. And we know we don't have a saddle. So then, yeah. Like theorem 16, what the f is theorem 16? Sorry, I looked at this earlier and I was like, it's clearly didn't look hard enough. What is theorem 16? That's cool. I didn't know that. I guess that makes sense. Well, it totally makes sense. Cool. So theorem 16 says, if the determinant's positive and the trace is negative, you have stability. Is my trace negative? I don't know. Maybe. I don't know. I've got negative gamma minus. Oh, yeah, it is. Because look, because this part here, we know that that part's positive. So I have a negative gamma minus a positive number. So it's got to be negative. So think about this for a second. The trace is negative. The determinant's positive. We know we don't have a saddle. Let me remind you of the solution to the quadratic formula if you're using the trace determinants. So the solution, my eigenvalues would be the trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2. So for sure, we don't have a saddle because the determinant is positive. But you know what else is true? Since our determinant is positive, whatever is in here, and I want you to look here for a second, whatever I have inside my square root here is smaller than the trace squared. Trace squared minus a positive number, smaller than the trace squared. So whatever I have here, the square root of the trace squared minus 4 delta is smaller than the trace. I guess I should technically say it's smaller than the absolute value of the trace. So if the trace is negative and you add a number that's smaller than its absolute value, it's still negative. And if you subtract a number that's smaller than its absolute value, it's definitely still negative. Or if things aren't real and we're complex, because right, we could be complex, maybe this is too big over here, we still have stability because our trace is negative. And you have a negative real part plus or minus the square root of a negative number, which means we would have a stable spiral. So cool, this is great. I learned something today. That if you have a negative trace and a positive determinant, you are for sure guaranteed stability. That's neat. I'm glad I learned something today. Because either you'll have real eigenvalues and they'll both be negative, so you'll have a stable node, or you'll have imaginary complex eigenvalues and the real parts will both be negative, so you'll have a stable spiral. But we don't even care if it's a spiral or a node, we just care that it's stable. Cool, I like that. By the way, so that is theorem 16 in your textbook. That's on page 671. it says, suppose you got some equilibrium and the determinant is positive and the trace is negative, then the equilibrium is locally stable. Right? That local word is important. Doesn't mean you got stability everywhere. It just means close to that equilibrium, you have stability. Cool. Yeah. And then if either of those is not true, you have instability. If the determinant's negative, you have a saddle, which for sure means you're unstable. And if the trace is positive, then you're either going to have, well, and the determinant's negative, then you're going to have either an unstable spiral or an unstable, no. Neat, super neat. All right, yeah, cool. Well, so that problem was not my favorite, as you might have guessed, but I feel like we learned something. I feel like I learned something. Hopefully you all feel like you learned something. We got a few minutes left. What can I say in a few minutes? Not a lot. These problems always take so much effort. Had something though. Let's see here. 1 second. Not you. Yeah, you're not great though. We did you last time. Sure. Can we do that one? I don't think so. Cool. Yeah, we'll look at this one. We got a few minutes. Let's at least, we'll start this one. So let's say we want to find, I'll just write this as easily as possible. Analyze the equilibria of the following system. dx1 dt is equal to negative 5x1 plus x1 times x2. dx2 dt is equal to x2 minus 5x1 times x2. Definitely non-linear because you got x1 times x2. So we're going to start off by finding the equilibria, set both of those equal to 0. So we're going to have negative 5x1 plus x1 times x2 equal to 0. Try to make this as easy on yourself as you can. I'm going to factor out an x1. I'm going to have a negative 5 plus x2 equal to 0. So either x1 equals 0 or x2 equals 5. Be careful. 0, 5 is not an equilibrium. Just like way before when we were finding critical points of functions of two variables and you got two solutions from one thing being 0, that point was usually not a critical point. Because if I plug in 0 for x1 and 5 for x2, in this other equation here, I would get 5 minus 0, which isn't 0. Right? You're looking for simultaneous solutions to both equations. So that's our first equation. The second equation has to equal 0 is x2 minus 5x1 times x2 has to equal 0. When we factor out x2, you're left with 1 minus 5x1 equals 0. So you're either getting x2 equal to 0 or x1 equal to 1/5. And then since these were each able to be solved without having to plug one to the other, we can just pair them up, meaning x1 could be 0 and x2 could be 0. Great, there's one equilibrium. Or now be careful here. I can't say x1 could be 0 and x1 is 1/5. That doesn't make any sense. The other pairing is x2 is 5 and x1 is 1/5. So that's my other one. So those are my equilibria. And then we find the Jacobian, and then we plug in the points. So Jacobian's not too terrible here. I think we can cram it in. I know we've got like a minute left, but we'll do it anyway. So the Jacobian real quick, like here. Here's my first thing. I'm taking the derivative with respect to x1. I'm going to get negative 5 plus x2. Derivative with respect to x2, I'm going to get 0 plus x1. Second equation, derivative with respect to x1, I'm going to get negative 5x2. Derivative with respect to x2, I'm going to get 1 minus 5x1. And then we're going to plug in our 2 points. We're going to use the cool new theorem we just talked about. Probably. Maybe. I don't know. If I plug in 0, 0, I'm going to get negative 5, 0, 0, 1. Okay, you probably don't need to use the cool theorem we just talked about, because what are my eigenvalues here? Or, yeah, what are my eigenvalues here? Which means we have stability or instability. Right, because it would be a saddle. Right, so we know it's unstable because the determinant is negative. Yeah, the determinant is negative, right? Yeah. Negative 5 minus 1 minus 0. Yeah. unstable. Determinant is equal to -5, which is, and then for the other one, which I forgot what it was, 1/5, 5. We plug that in and we get -5 plus 5 is 0. 1/5. -5 times 5 is -25. And then 1 minus 1, 0. Okay, so here my trace is 0. I don't think you can use that theorem, unfortunately. Right? The theorem said trace had to be positive, not equal to 0. So here I find the eigenvalues, and let me just look at my notes here. Yeah. Yeah, this one's funky. Sorry. I don't love that. I guess you could, so, yeah. Yeah, so let's just, sorry, my determinant's 5, the trace is 0. It's hard to say stable because even though, so if you actually found the eigenvalues, maybe lambda equals 0 plus or minus the square root of 0 minus 4 times 1 times 5, or 2, that's plus or minus the square root of -20. Those would be both imaginary. So you would have, if this was actually the system, you'd have a stable center. But since we're talking about local stability, it's a little dicier. The notes that I've written here are that even though this appears to be a neutral spiral, we can't make this conclusion because we are approximately this thing in this region, but we're not exactly that all the time. So